The next machinery fault that is associated to non-sync vibration is beating. Beating can occur at any frequency when there are two closely spaced excitations having relatively similar vibration amplitude comes together. Beating can be rectified by reducing or removing one of the excitations. For example, for two identical machines sitting close to each other and having a small variation in rotating speed, you'll be giving beating effect, reducing the dominancy of the running speed component of one of the unit, for example, through balancing or increasing the damping, could reduce this effect. Beating is basically the summations of two vibration signals that are very close in frequency. It will cause the amplitude of vibrations to fluctuate over time. When the amplitude of two signals are in phase, the amplitude will be added up and become maximum. Whereas at one time, when the amplitude of two signals are out of phase or in opposite directions, they will cancel out each other, leaving to minimum amplitude. In time domain plot, the vibration will go maximum and minimum over time. The period between the two successive maximum amplitude or minimum amplitude is called beat period. It is equal to the spacing between the two frequencies. For example, a 99.5 Hz and 100 Hz vibration come together. The beat period is 1 over 0.5 Hz or 2 seconds. It means the vibration will go maximum, minimum, and then maximum in 2 seconds. In frequency averaging, in the case of the FFT resolution is not fine enough to split the two closely spaced frequencies, the Lie spectral plot will show maximum and minimum amplitude over time. In the case the FFT resolution is fine enough to separate the two close frequencies, the frequency difference between the two frequency components indicate the beat frequency. In vibration data collections, it is recommended that the data acquisition time for each block is larger than the beat periods so that the signal captured in each block is consistent before sending for averaging. Or else, the amplitude will be fluctuating in each block and giving non-consistent amplitude even with averaging. In the case study of beating example, it was noted that the steam turbine input shaft speed at 6,150 rpm or equal to 102.5 Hz came close to the generator 4-time output speed as well as a 2-time electrical line frequency at 6,000 rpm or 100 Hz. Next, non-synchronous vibration fault is resonance. It occurs when the excitation frequency coincides with or near to one of the system or structure's natural frequency. Although the excitation frequency could be from the 1-time RPM, but it could be also from any other excitation frequency which are not related to the synchronous vibrations. As we have discussed in previous topics, resonance happens because of the system undergo a low or no resistance, meaning the system or structure lose its ability to resist motions and resulting in large vibration which would cause premature failure to machinery. In rectifying resonance issues, considering on the structure design modification by stiffening or adding mass with the aim to shift the natural frequency away from the excitation frequency could solve the problem. Or if the excitation frequency is allowed to change, then changing the excitation frequency away from the natural frequency will be the alternative. In rectifying resonance issues through structural design modifications, one first needs to understand the dynamic behavior of the structure or system through the determination of dynamic characteristics of the system. The dynamic characteristics of a system or structure comprise of the natural frequency, mode shapes, and damping. And these three parameters are heavily dependent on the geometrical properties, material properties, and boundary conditions. If one wants to shift the natural frequency of the system, one first needs to know the natural frequency, and with the information of geometrical material properties and boundary conditions, one can decide how to shift the natural frequency. For example, stiffening it by using higher stiffened material, or adding the weight of the system by using a larger geometry, and etc. Some techniques could be used to determine the resonance or natural frequencies. They are bump tests, where a force will apply on the structures and the response due to this force will give the natural peak or frequency. Body plot or magnitude and phase plot is usually used during the run up or coast down of the machine in transient analysis. These machines will speed up, and the one-time RPM vibration amplitude and the phase were plotted over the increasing or decreasing speed. When the system passes through its first critical speed, or the running speed, coincide with the first natural frequency, high one-time RPM vibrations will be plotted. And at this instant, there is a sharp 90-degree phase change. Looking into the entire plot will indicate where is the first critical speed or natural frequency. Next, waterfall or cascade plot is also used during transient analysis. The full spectrum is plotted over the changing speed or time. Through this plot, one can identify the first critical speed or natural frequency in which the one-time RPM frequency component is at its maximum. Model analysis is a more complex version of bump test where a known input force is applied. In this case, the input and output are known, and therefore a full transfer functions of the system could be determined, and a more complete analysis could be achieved. Finally, Nyquist plot or polar plot is another method to represent the vibration magnitude and phase from that transient analysis. This plot could trace a circle in the resonant frequency region due to the phase change in this region. A body plot can help to identify the resonance speed or resonant frequency of a rotor, or examine the rotor dynamic on an order basis. Model analysis is a complete dynamic behavior test which can fully determine the dynamic characteristics, namely the natural frequency, damping, and mode shapes. Cavitation is another force that is associated to the non-synchronous vibration energy. It happens due to the sudden drop in the liquid or gas pressures at the suction side of the pump, creating a vacuum conditions. If the fluids or gas inside the pump falls below the vapor pressures, cavitation will occur. There are two types of cavitations, namely classic cavitations and recirculation cavitations. In classic cavitations, formations of bubbles at the impeller eyes due to the pressure drop caused by frictions or velocities. The bubbles are swept outward along the impeller, causing change in liquid velocity, which result the bubble to collapse. Implosions of the bubbles or random noises cause small wear on the impeller surface. Whereas recirculation cavitations usually happens where there is a formation of vapor filled pockets, generally on the suction side. Eddy current formed at the eye of the impeller reduce the flow channel size and thus increase the fluid velocity, thereby reducing the fluid pressures. If the fluid pressure is lower than the vapor pressures, cavitation will occur. Other causes of cavitation could be vein pass symptom due to small clearance between the impeller tips and the pump volume, increase in fluid temperatures, and air ingestions at suction site. Cavitation could cause the pumping performance of the pumps drops, poor flow capacities, and could also cause damage to impellers and seals, lead to primary faults such as imbalance. In vibrations, implosions of bubbles on the impeller surface and pump volume would create a random vibrations where it is interpreted in frequency domain. A random broadband high frequency vibration signature will be observed in the spectrum. The random vibrations could also excite the pump casing, giving the resonance or natural frequency of the pump, in which sometimes non-synchronous frequency components, which are the natural frequency of the pump, could be observed in the spectrum. Alternatively, noise measurement can be employed in detecting cavitations. A serious wear on the impeller due to cavitations will result in the increase of one-time RPM vibration amplitude, indicating the imbalance symptom. Defects in belt drive usually fall under non-synchronous vibration components. Common defects in belt drive are the belt pulley misalignment, eccentric pulley, belt flap or resonance, and mismatched, worn, or loose belts. The belt drive formulation is derived as output speed times the inner diameter of the output is equal to the input speed times the inner diameter of the input. Belt pulley misalignment such as offset, pigeon toe, and the angle faults will show faults characteristics of high one-time output or input speed in the vibration spectrum. Usually it happens in axial directions or along shaft directions, and generally it happens at the driven side. Whereas for eccentric pulleys, the vibration spectrum will show high one-time RPM of the eccentric pulley in the radial directions. If there is belt flap or resonance, it happens that the belt natural frequency coincide or near to the input or output speed. In the radial directions vibration spectrum, the one-time RPM will come close to the belt resonance frequency, giving two closely spaced frequency components or sometimes broad one-time RPM peak. In this case, usually increase the belt tension will solve the problem.